Hey everybody, I'm Drew Gallatin and I work for Netflix on the OpenConnect CDN, and I'm a kernel engineer that works on the operating system kernel that runs on our CDN servers. Basically, we call them OpenConnect appliances, so if you hear me say OCA, I mean CDN server. And I'm here to talk about sort of a greatest hits of a bunch of optimizations that have allowed us to be super efficient. And so I've made some progress since Dan asked me to do this talk. So everything in this talk is going to be framed in the terms of 800 gig rather than 400 gig. So basically, we're really efficient with our CDN serving, and the reason why is because we have an easy job. We serve only static files. We have a transcoding team that pre-transcodes all of our assets, and everything is deployed already transcoded, so everything we do is just serve big files out on the web. So that greatly simplifies our workload. And our stack is FreeBSD, not Linux, but FreeBSD, Nginx, and we try to serve everything via send file. You know, traditional web server running in user space, no DPDK, no SPDK, just standard stuff that people have been doing since the 90s. And so here's kind of a timeline of some of the most important optimizations that we've had. We haven't done all these ourselves. In fact, most of these were done in collaboration with external community members in the FreeBSD community and the Nginx community and different vendors. So the first thing up I'm going to talk about is asynchronous send file. And so what's send file? It's something that came out in the 90s. Basically, it's a way to tell, for a web server to tell the kernel, take this file and send it on this socket. And it's very efficient because it eliminates the need for data copies. And so now you're going to see this. This is the diagram you're going to see all through the presentation. Basically, what we're doing is we're showing the data flow into system memory from NVMe or disks or whatever you want, some kind of storage, and then out on the network card. And notice the CPU is not really touching the data very much. He's kind of just a traffic director. So the problem with send file traditionally has been that reads can block Nginx. And we were doing some hacks with AIO to try to get around that. Other people have used thread pools to try to get around that. But we found that stuff doesn't scale very well for us. And so what asynchronous send file does is it takes advantage of some quirks about the way FreeBSD works to make send file essentially fire and forget. So what happens is we basically allocate empty buffers in the TCP socket buffers for a client, and we tell the disk, hey, when you bring this stuff in from disk, put it in these empty buffers that we got for you. And then once we've done that, Nginx goes on his way, and later when the disk fills those buffers, it notifies the TCP stack that he can send things. And so a picture's worth 1,000 words. And so in this picture, whoops, I was advancing. Here's the laser pointer. We have Nginx at the bottom, storage, the socket buffer, TCP sending on the network is represented by this red line since there's nothing to send. So Nginx gets a request for a media file, and he starts allocating space in the socket buffers, and he tells the disks to get the data that we want. Once we've allocated things in the socket buffers, those red stoplights indicate that things aren't ready. And then once they are ready, the disk interrupt handler then marks them ready. Those are those green lights, and things don't always happen in order. So we still can't send anything because the things at the front didn't come in yet. Now when they do, TCP can start sending and sends things out in the wire. And just that little bit of cleverness took us from about 23 gigabits a second to 36 gigabits a second back in 2014 using a really old Xeon, which was pretty current then. And so now I'm going to move on to the next thing, which is kernel TLS. So first, what's TLS? I mean, if you've used the web in the last 10 years, TLS is what encrypts everything between web servers and clients. You know, people used to call it SSL. It's that little padlock in your web browser. So we had this mandate that we had to start encrypting communications between our servers and our clients. And the problem with that is that completely breaks all these nice optimizations that we've done around send file. Because when you're encrypting things, traditionally the way you would encrypt things is you would read things in from the disk, and then you would copy them into user space. The web server and OpenSSL would read them, encrypt them, write them back to user space memory, and then finally write them into the kernel, and the kernel can finally send it. And see, all these vertical arrows, this is just wasted memory bandwidth. And you take a machine that could serve 100 gigs, and you take it down to 30, 40 gigs doing this. So Netflix started working on kernel TLS in 2014, 2015. And basically, the idea is to eliminate those copies that I was just highlighting. Basically, it restores our old data flow. And the way it works is basically you hand TLS state to the kernel after doing all the handshakes and stuff in user space, and the kernel just does the bulk crypto. And the cool thing is we can add it as an extra stage on asynchronous send file. So this looks pretty much the same as the last diagram, except we have this new crypto state here represented by the padlock. So again, Nginx gets a request now for a TLS encrypted session where he allocates space in the socket buffers and tells the disks to start bringing things in. Now we're not ready. The disks finally bring their stuff in, and instead of marking them green and ready to go, TCP is still waiting because they're yellow because we haven't encrypted them yet. Now we encrypt them, and now we can start sending them on the wire. So the cool thing about that is it just kind of nicely dovetails. And the other cool thing about it is that now we still have these vertical arrows because the CPU is still reading the data for encryption and writing it back, but we've basically cut our memory bandwidth requirements almost in half because we're not doing these extra boundary crossings in and out of the kernel. And so now the data flow is disks to memory, CPU reads to encrypt, writes, and then back out of the network card. And so the next thing we worked on, which we thought we were going to need, but due to inline KTLS and also due to increases in speeds and feeds in terms of PCI Express and DDR5 and things like that, we have never actually needed it, but we use it for forward-facing experiments like this 800G stuff I'm going to talk about, is NUMA. So, by the way, the clock down here is not running. Excuse me? The clock down here is not running. Okay. So anyway, the NUMA stands for Non-Uniform Memory Architecture. And basically, it means using multi-socket machines as servers. Up until this point, we'd never tried to serve on a multi-socket machine. So basically, back in the day, if you were to add more CPUs to a system, there'd be some shared crossbar, some bus, and you just plug things in, and it wouldn't matter where you plug things in. Everything had equal access to everything else. But with NUMA, when you add sockets to a system, basically these sockets can be far away from other resources on one socket can be far away from resources on another socket. And so, if you're on the CPU down here, you don't want to be pulling stuff from this memory because you cross the NUMA bus, which is represented by this red line. You really want to be on this side. And so we call these things NUMA domains, these areas where locality is important. And what we want to do is we want to keep as much of the 400 gigabytes a second of bulk data off the NUMA fabric as possible. And so now we're going to start off with a naive data flow model where we have two NUMA nodes. And let's see what could go wrong. So we have a connection coming in down at the bottom, and we decide, oh, we want to read things out from disk into memory, but we weren't paying attention, so we put it in the wrong NUMA domain, crossed the NUMA bus. Then we encrypted it with the wrong CPU, and then we wrote it back again to the wrong memory. Okay, and so we've crossed the NUMA bus 3 times at this point, and then we sent it out on this network card down here, which is another NUMA bus crossing. And so when you cross the NUMA bus that many times, which can happen if you're doing things randomly, you exceed the fabric bandwidth, and it just doesn't work. So in the best case, really what you want to do is you want to read from the disks into local memory, encrypt it right on that CPU, and send it out on the wire. And so you never cross it. It's perfectly scalable, and that's something that's really hard to pull off in the real world. So I came up with 2 mechanisms to try to sort of impose some order on this chaos. I call them disk-centric siloing or network-centric siloing. So I'm going to focus mostly on network-centric siloing because that's the only thing I would feel comfortable running in production at this point. So with network-centric siloing, like let's say we have a connection come in on this NIC down here. We keep track of which NIC the connection is local to, and then we make all of the resources local to the connection. So we read we read things from these disks and pull them down into this memory. And then we do the crypto local to the network card, and then we store the result in the memory local to the network card and send it out in the network card. And so this is the worst case here, where we cross the NUMA bus just once. Now, with disk-centric siloing, it's pretty similar. We again have the connection coming in at this network card at the bottom. So with disk-centric siloing, we allocate the memory backing things and do the crypto on the node that's local to the disk. And so here we keep doing that, but now we're going to send it out on the network card that he came in on, which is again another NUMA bus crossing. So we've got a NUMA bus crossing this way as well. Now, there's another thing which I'm calling strict disk-centric siloing, where basically we still have the network connection coming in at the bottom here, but we keep the bulk data off by retagging the network connection and having the network connection go out on, having the network traffic go out on this card. That's complicated and bad for a variety of reasons that I don't have time to get into. At least I don't think I do. And I'd prefer never to run this in production, but it definitely has the best, it could potentially have the best performance because we're not crossing the NUMA bus. And so now something that we actually do use in production is inline hardware kernel TLS, or FreeBSD calls it NIC KTLS. So why do we want to offload KTLS? First, this is a flame graph of our CPU use. If I remember right, this was an AMD ROM doing around 240 gigabits a second. And all the area in the red is CPU time that we spend doing crypto. And all the other stuff is, Nginx, TCP, all that kind of stuff. So it sure would be nice if we could just, get rid of this, what's inside this red circle. The other thing is we have these vertical green arrows that we want to get rid of. And by having the CPU do the encryption, we're basically doubling our memory bandwidth costs. So wouldn't it be nice if we could do it in hardware? And we talked to a bunch of NIC vendors starting in 2016, 2017. And Mellanox was also interested in doing this, and we stayed in touch, and as they evolved their APIs, and they got us some prototype firmware for their ConnectX 6DX just before the pandemic in early 2020. And Mellanox and Netflix iterated for about 2 years before we were able to put it into production, and we finally got it into production in the last quarter. So what is NIC KTLS, or inline hardware KTLS? Basically, it's kernel TLS taken a step further. The TLS sessions is established in user space like kernel TLS, but then when we move the crypto to the kernel just kind of does a hot potato and moves it down to the NIC. And so basically, the TLS records are encrypted by the NIC as they flow through the NIC already. And the nice thing is, like I was saying, is that eliminates these vertical arrows and gets us back to that same picture we had 10 minutes ago at the beginning of the presentation before we had to worry about TLS, where essentially we've just got the simple data flow of in from disks into memory and then out on the network card. The CPU is his loafing. He's like sitting around reading a book, not doing much, just kind of directing traffic. So these particular NICs, they offload TLS 1.2 and 1.3 for AES GCM, and that's about 99.9 repeating percent of our workload. And the cool thing about these NICs, which their competitors can't say, is that they retain TLS state inside of a TLS record. And this is important for us because we do a lot of innovation with the TCP stack, and so the TCP stack wants to have really fine-grained control of what he sends. And so that means that the TCP stack can leave off sending, say, 2 segments into a 16K TLS record, and then come around when he gets the ACK and send the next 2K segments, and the NIC doesn't make anybody do any extra work. Because the NIC retains the crypto state inside the TLS record. Now, the problem, though, is that if a packet's sent out of order, like if TCP loses a packet and we need to do a retransmit, the NIC has to re-DMA the entire TLS record up until what was lost, up until including what was lost, in order to send it. So again, sometimes a picture's worth 1,000 words. This is similar to my last diagram. Up here, we have basically a host socket buffer, and I've annotated the TCP segment offsets. And we have a crude representation of PCI Express bus. The NIC is down here, and then here's the network. And so when the NIC goes to send, say, the first half of the TLS record, the red arrows are him DMAing it down across the PCI Express bus, then he encrypts it, and then he sends it out on the wire. Now, the TCP comes around and wants to send the last half of the TLS record, so the NIC fetches those segments, encrypts them, and then sends them on the wire. That's all simple. That's exactly how things always used to work before TLS, before any of these fancy offloads. The problem though is TCP retransmits. So let's say that we lost this segment and TCP says, hey, let's resend this segment. Well, when that happens, the NIC, he can't just send this segment. In order to encrypt it, he has to sort of resynchronize his crypto state, which means he needs to grab pretty much the entire TLS record up until the one he wants to send. Then he encrypts everything up until that. He extracts the last segment, and then he sends it on just that one segment on the wire. And so now I'm going to talk about the fun stuff, where we put everything together, which is the 800 gig stuff. This is just a prototype. We're not planning on putting this in production anytime soon. This is a dual socket machine, which we'd never put into production. It's a Dell with 2 AMD Milan CPUs. And the interesting thing about this setup is that there are 3 XGMI links between the sockets and not 4. So the issue we had when we were speccing this machine and shopping for this machine is that we couldn't find any. Basically, AMD trades off PCI Express resources for XGMI resources. And we couldn't find a motherboard that both had enough PCI lanes exposed so we could have enough NVMe and enough network cards, and had 4 XGMI links between the sockets. So we're stuck with something that's got 3 links. It's got 512 gigs of memory, 4 Mellanox dual port 100 gig NICs, and 16 Intel Gen 4 by 4 NVMe drives. So the initial results are quite underwhelming. We ran in 1 node per socket mode. We ran with network siloing, and the CPUs were almost entirely idle. I think the CPU load was like 20% or 15%. And our AMD technical folks that we talk to all the time guessed that the XGMI link was downclocking and downlinking to X2. And so we set the, we hard-coded the XGMI speed and width and disabled all this dynamic stuff. And once we did that, we got up to about 500 gigabits a second. And this is, again, network-centric siloing. And the key here is that the NVMe drive is DMAing stuff into the NIC's NUMA node because it's network-centric siloing. And it turns out that when you've got 3 XGMI links and not 4, things are not hashed very evenly. And so what happened was one of the XGMI links was nearly maxed out and the other 2 were pretty much idle. And talking to AMD, we realized that basically I/O traffic is hashed to the XGMI link based on what quadrant the guy who's doing the DMA is coming from. So if you remember, AMD server CPUs have these chiplets, and there's essentially 4 I/O quadrants. Matters a lot less now than it used to in their first generation when you almost had to treat the chip itself as NUMA. But for this, it actually matters which of the 4 quadrants your I/O devices are in. So what I did was I switched to disk-centric siloing. So by basically flipping things and having the disk's DMA to a local buffer. And so now it's the NICs that are doing DMA across the NUMA fabric. And that was much better. The XGMI hashing was pretty much even for 2 and a little bit low for 1. And that gets us to about 670 gigabits a second. Now that's problematic and not ready for production for a variety of reasons. It's mostly problematic because we have this strategy where we basically tell the kernel, hey, free everything unless it's something we think we're going to need later. And there's a daemon that figures out, what these things we think we're going to need later are, and it basically sort of locks them in memory. It doesn't really lock them in memory because the kernel can get rid of them if it really wants to. But the issue is that if we have, like, say, a super popular release, and the files all landed on NVMe drives that are on, say, NUMA Node 1, then let's say it's the first weekend of Squid Game or something. It's just going viral and it's super popular. We're going to want to leave a lot of that stuff in memory. And if it's all on one NUMA node, this daemon hasn't been updated to be NUMA aware, and it probably never will because we're not going to run this in production. And so it's going to put, say, 400 gigabytes worth of popular content that's all in this one NUMA node, trying to put it in memory. And so that node is going to be thrashing, and the page daemon is going to be thrashing, trying to evict this stuff, and we're going to be trying to put it back in, and it's going to be a mess because this thing thinks there's 500 gigs of flat memory when really there's 256 gigs for each domain. So at any rate, I got a good result one day, but if there's some really popular viral thing, I can't promise that would be a good result on another day. So basically, at this point, I decided, well, what the heck, let's try strict disk-centric siloing. It doesn't look like the XGMI links are a problem, but it can't hurt to just take the traffic off of them. And so basically, it's just what I talked about in the diagram. We're moving the egress NIC to be close to where the content is. And so once we did that, we got to about 720 gigabits a second. And I forgot the exact CPU. I think it's in the 50% range. And we're limited by network interface card output drops, not by the CPU. And so there's a bunch of different causes for those drops. One of the causes is uneven loading on the network interface cards, because essentially when you are doing disk-centric siloing, you're hashing based on the content distribution. You're hashing now with strict disk-centric siloing. Instead of hashing traffic to a network card based on LACP, which is a hash of TCP port numbers and IP addresses, which have a huge amount of entropy, so you wind up with an even number of sessions on all the different NICs. If you hash based on content that people want, and there's super popular content on one node, it's the same thing where I was talking about the memory lock daemon being overloaded. You end up with now with strict siloing, you end up with a network card overloading. And like in this example, I think some of the network cards were doing like 95 gigabits and some were doing 85 gigabits, just because one node had slightly more popular content than the other. And so here's a slightly pretty picture from our internal graph system showing this box doing 720 gigs for over an hour without any issues. And so at this point, I just want to say that I may not have emphasized this in the talk, but all these optimizations weren't done by me. In fact, many of them were done by other people. Async send file was done before I got to Netflix. It was done by mostly by Gleb Smirnov, who was at the time an employee of Nginx, and now he's at Netflix. And Konstantin is a FreeBSD committer, VM guru, who was very helpful with this. Igor is one of the Nginx people, and Jeff Roberson and Scott Long are from the FreeBSD and Netflix side. So for kernel TLS, the initial implementation was done by Randall Stewart and John Mark Gurney. And Scott Long kind of basically had the idea for it. I did the second system implementation, which hooked it into the async send file and got into a state where it could be upstreamed into FreeBSD. And John Baldwin carried it over the finish line and upstreamed it into FreeBSD and ported all of our nasty OpenSSL patches into OpenSSL and all that kind of stuff. For NUMA, this was basically all me in terms of the network locality, network siloing. Jeff Roberson and Mark Johnston from FreeBSD helped out a lot with making the FreeBSD kernel in general more NUMA aware and more efficient for NUMA. And for inline hardware kernel TLS, I have to say that the Mellanox was a huge help. Between them and John Baldwin, who works for us as a contractor, we were able to get that upstreamed as well. And I need to mention Boris Pasimi from Mellanox. KTLS was his baby on the Mellanox side, and he's carried it across the finish line on the Linux side. And so I think that's about all I have. Oh yeah, I need to give credits for the experimental 800 gig host. So I want to thank Warren Harroup. He's one of the hardware guys at Netflix who coordinated the whole thing. MBX and Dell were the integrators. And it was, again, AMD 7713 Milan CPUs in a Dell PowerEdge 7525 with Mellanox NVIDIA ConnectX 6 DX NICs and Intel NVMe. And so I didn't think I'd have time for questions. I guess I squeezed things tighter than I thought, but I've got about 5 minutes if anybody wants to ask questions. So I kind of sprung that on you. I apologize. I think the question was, do we have any plans for QUIC? Our client team is interested in it. We mostly have the feeling that we can control the TCP stack well enough that we don't need it. Right now, QUIC would be an efficiency disaster for us because you lose, 30 years of hardware optimizations that, like TSO, this crypto offload, you lose all kinds of stuff when you do QUIC. So our efficiency, 800 gigs would probably go to 200 gigs.
And what about Chacha Poly?
I'm sorry, I didn't catch the last word.
Chacha Poly.
Chacha Poly. That's actually interesting. Our client team thought it's another thing our client team thought they really, really, really wanted. And we paid a contractor to enable Chacha Poly in FreeBSD. It's enabled upstream, so our client team got us Chacha Poly KTLS support in FreeBSD. It's massively more expensive on the server side, and in our A/B testing, it did not provide any measurable benefit on the client side. It could be that they may want to redo those tests in the future, but this was maybe 6 months or a year ago, and it just didn't provide the benefit they were looking for.
How many disks and how big are the disks that you're using?
I believe this is 16. I believe it's 16 8-terabyte disks, but I'm not 100% certain. If I can look it up after you come see me after the talk and I can look it up. All right, if that's it, I'll relinquish the stage.